Hi, this is a design for a scientific talk which I had made quite a long time back. I was inspired by, let me get the book, excuse me, please, by, by the Britannica Guide to the 100 most influential scientists. And there's Albert Einstein on the cover. It has an introduction by John Gribbin, and I chose 10 scientists for a talk, but then I was doing some research today and I decided I would stop at 6 because I came up with additional thoughts apart from what information is available on the internet. And I'll resume. There's another talk which I've formulated, which I've designed, not yet formulated, and it has 5 scientists. Now, here we begin with Pythagoras. You're all familiar with the Pythagoras theorem. It's to do with right angled triangles. The square on the hypotenuse is equal to the sum on the squares on the other two sides. This is probably used in building buildings and getting the dimensions on rooms right, on square rooms right, I presume. But he also came up with a tetractys, which is a triangle, of 10 points. So now this is a tetractys. So we have 3 plus 3, 6, then 4. So this is a tetractys, 3 plus 3, 6 plus 4, 10 points. All right. Now, I thought that this could be a matrix, 1 by 1, 2 by 1, 3 by 1, no columns, rows, 4 by 1. So there are 4 matrices. And if you were to take a transpose of the matrix, you would get a straight line. So you would take a transpose, you would get just 10 points continuously aligning themselves in a straight line. Now, if you were to multiply by a scalar quantity, you would get 2. So I'm going to multiply by 2 maybe. And then the same thing, you would get exactly twice the number of points. It's a sort of a symmetry which is involved in the tetractys. So you could multiply by 2, and then you would get, how many points do we have? 3, 3, 6, plus 4, 10, plus 2, 12, plus 8. And this is again a triangle. I haven't written it, but I'm holding it. It's not very symmetrical because I haven't drawn it symmetrically. So those were my thoughts about a tetractys. Transpose of the matrices forming the tetractys, and multiplication of by a scalar quantity each of the matrices comprising the tetractys. That is on the tetractys. Next, and also Pythagoras came up with a branch of epistemology. I looked up epistemology in the dictionary, and it's the branch of philosophy. It's such a lovely definition. Branch of philosophy which deals with knowledge. I'm an epistemologist, means I'm an extremely knowledgeable person. I'm not. I aim. With the internet, we all are knowledgeable, right? I mean, it's all in 1 second and you get it. But there are some times when internet begs to differ from magazines and books. Of course, books come first. Books always come first. And I did mention this to, because I've been live streaming on Facebook, to Mark Zuckerberg, because in The Economist, to created DNA bases, a synthesized DNA basis, didn't show up on an internet search or had a different formula. I forget how that meant. And then DNA base was wrong. It didn't connect to a deoxyribose molecule. It was just the pyrimidine and the purine are all over the internet. You remember DNA molecule, deoxyribose has to come, and only then is it a complete molecule. Anyways, that was right in James D. Watson's Molecular Biology of the Gene. So that's an aside. Now we are done with Pythagoras. I'm going to go to Hippocrates. He came up a long time back. This is years ago, 500 BC. He said diet and exercise are important for a healthy, functioning body. And then he came up with surgery, which is fascinating. I'm originally from India, and of course, Ayurveda comes from India, Ayurvedic medicine, and there were doctors back from then, Shushruta and Charaka, who lived in the Indus Valley civilization, even before this, before the Roman civilization. Hippocrates is Roman. Yes, yeah, was it yesterday I thanked all the Greek mathematicians and scientists and engineers? And today I'm thanking all the Roman scientists and mathematicians and engineers. So now let me get a tissue and erase this. And now Hippocrates the Hippocratic Oath deals with both philosophical and practical aspects of medicine. It not only, again, once again, reiterating, it not only deals with abstract principles, but practical methods such as removing stones and surgery, and also a practical method for a doctor to gain fame is to aid his teacher financially, professor and teacher financially. Now, as an engineer, I did give my heart and soul's work to my supervisors and teachers and philosophers, my high school teachers, my even my nursery teachers and all of them who taught me. My mother, of course, must have taught me the alphabet, the English alphabet. So all of them, because they were all my teachers. But there is an interesting thing because my supervisor, I suspect, didn't wish the best for me. Bradley Isabel, he belongs to the Department of Chemical Engineering and Applied Chemistry, University of Toronto, and he, I suspect, was not as innocent as he seemed. All right, and I sort of look at this with sadness because I could have helped him out so much more by getting him to move ahead in life as well. In life, because he's very ahead. He's on the web. You can look him up. He has a number of papers and book and etc. to his patents as well. Anyways, so there is this interesting story of Ekalavya in the Mahabharata. It's an epic. It's an epic. There are two epics in Indian mythology, Ramayana and the Mahabharata. And the Mahabharata, there are the poor rich class. That's how you put them, and they're the aristocrats who are poor, but they have a wonderful teacher. And aristocrats in general have a lot of loyalty from the intellectuals, from because they could get them ahead at some point in time, and figuratively speaking, because there is no class system in Canada. Canada is above all that. Everybody is granted equality, etc. But hierarchically speaking, Prime Minister Justin Trudeau is aristocracy, and I'm hoping because he's also an intellectual, of course. Needless to say, he's the Prime Minister. It must be, but I'm more qualified than him, leastways in science and engineering, and I hope that he will further my advance as an intellectual. So, anyways, coming back to Ekalavya, he used to practice archery with the figure of the teacher of the poor aristocrats, five poor aristocrats, the Pandava brothers. It is irrelevant here, but I just thought I would mention it. And the teacher was Drona, and Drona saw him practice archery. He was better than his students. So he called Ekalavya when nobody was around and said, "You've been practicing with my idol, etc." And Eklavya was thrilled. My teacher, please, what do you want from me? He was fantastic at archery, could get any target. And Drona, he had to be worse than his poor aristocrat students. See, he said, "I want your thumb as my uh, thank you uh, offering." As your thank you offering, because you've advanced so much. So Eklavya had to give away his thumb. Obviously, he never probably didn't do any more archery at all. So that is what I used to tease my supervisor, but not to his face. To my friends, I would tease him because I never did get back. But I went to corporate culture, so maybe my supervisor resented that no professor has ever worked in a company. There are a few of them, of course, who come from companies. But for a short while, I worked in corporate culture. So Aigen Corporation, Ottawa. So it was okay. I guess it was all right. So, anyways, financial aid is important to teachers and professors, because medicine teachers who teach them are called professors. All right. So, anyways, third is Plato. It is Socrates, Plato, and Aristotle. Aristotle was the teacher of Alexander the Great. Plato spoke about soul. There are three aspects. They all spoke about soul, actually, I think. No, Aristotle. Plato and Aristotle. And soul, according to Plato, also has reason, has the ability to reason and assimilate, you can say, and theorize, etc., which is a fascinating aspect, see? Because I like to say I'm psyche. On my LinkedIn page as well, I say modern day psyche. Goodness as well, heart, soul has heart. And the other thing soul has, you can look it up, it's all on in the internet. So I forget. Now, Plato had a student, Theaetetus, and this is a bit of a mistake in the Britannica Guide by in the Britannica Guide, with an introduction by John Gribbin, um, it says Theaticus. It's minor mistake. So Theaetetus said that inside spheres there can be cubes and dodecahedrons and tetrahedrons, and octahedrons and icosahedrons, etc. Now, if you were to look at the simplest one, which is the cube, a cube sits in a sphere, and they did not know, I think, that the Earth, we lived on the surface of the Earth, and we lived on the surface of we live on the surface of the Earth. They assumed that human beings lived in the center of the Earth because they had no idea that. So they thought we were all inside, and later on, of course, astronomers, etc., came, and uh, or he didn't know, maybe this was Theaetetus, because when did Copernicus, Danish astronomer, right, came afterwards? Kepler, German, after. The Greek and the Roman civilizations were the first in Western culture. Anyways, so the interesting fact about a cube in a sphere is that if you were to look at the volume of a sphere, then it's 4 by 3 pi r cube, and of a cube, it's L cube. Equating the two, you get R is equal to L by cube root of 4 by 3 pi. It's probably a small number because the radius is higher than the length of the cube, than each side of a cube, than the length of each side of a cube. And a chord makes the length of the side of a cube. It can't be the diameter. Of course, this is all simple knowledge, but back then they did not have the tools we have. This is 2018, of course. Now Aristotle came up with the hierarchical system of classification of animals and plants, etc. So he said plants were at the lowest level because they had no intelligence. They have feeling though. If you, of course, you have uh, the stimulus. You apply a stimulus, it's going to react to the stimulus, the plant, um, and uh, uh, and um, and they have no feeling either. Plants, they have no feeling either. Stimulus, do they react? Sunlight, they grow. Music, they grow. This was all proven back in the 1990s. Back in the 1990s, or well, this probably dates back to my childhood days, 1970s, 19th childhood, 80s were my sixth to mm, music. Animals had some intelligence, so they came next, and human beings were at the top of the ladder, which is opposite to Linnaeus. Linnaeus came with vertebrates. He came up, he's the father of classification, right? Linnaeus is the father of classification. He came up with vertebrates and invertebrates based on backbones. And of course, but then the book said genus and species, and Aristotle didn't do it according to the internet. He didn't come up with genus and species. The phylum vertebrata, phylum invertebrata, and then genus. I used to know all this by heart, but I haven't done biology in a long time. Last I did biology was my 12th grade. So, anyways, that was about Aristotle. Aristotle also has stuff on soul, has his own thought processes on soul, which is very interesting to read. I urge you to look all this up in the library or on the internet. Or, we are the papers. They all have papers. I think most of them went away in the volcano at Pompeii, leastways the Roman civilization. Yeah. A lot of your research must have vanished then. Next, we have Einstein proved, it says, the book, the via his paper, via his experimental method, that atoms exist in all matter. Matter comprises of atoms. Dalton had come up with a theory, of course. We all know this in chemistry. And his paper on the movement of small particles suspended in stationary liquids required by the molecular kinetic theory. That's the paper by Einstein. He proved. But if you were to think about it, when water boils, you're seeing Brownian motion. Liquids are going far apart and they're beginning to move. So, because his theory was based on the fact that for you to apply heat to liquids, and I even watched a little short video on YouTube, which came up with a complicated equation. Now, I always swear by Newtonian physics. So you could say kinetic energy, each molecule, and this is in chemistry, is equal to Ke half mv square, half mv square. You all know this. So velocity, each of the atoms is going to develop, is going to start to move. So it's going to have velocity. And then at rest, before you started applying heat, it had the potential energy is equal to mgh, and height would be is related to even stationary pressure. What is the experiment called? The YouTube, the not manometer, manometric pressure. No, that's not right. There is a YouTube, and we all used to do this in our labs. The pressure has to have flow, but stationary liquids also have pressure. And pressure is equal to rho GH. So there, and then you add the flow rate, and there's you enter a realm of the realm of fluid mechanics. You need to go through engineering school to learn fluid mechanics. So simple equations can also explain Brownian motion. And then the next one is where I had a lot of fun. I experimented because I have a beaker and a conical flask. Both of them are not accurate. You need graduated cylinders. I experimented. So now Laplace and the chemist Lavoisier. Laplace, of course, from Laplace theorem, inverse Laplace. I connected you to him in one of my talks. I have the first talk I live streamed on Facebook to celebrate Black History Month. And I beg your pardon? They showed that respiration is a form of combustion. Which combustion, of course, is the reaction of oxygen to react to burn. Burning is combustion. When there is fuel, the fire is created, or smoke, or burning is combustion. All right, so that is combustion. And maybe they were not all that accurate because it was Einstein existed in 1905, right? Most of his research was done then, and after he was there till World War II, of course. But this was Laplace and Lavoisier. This was 1905, and I'm getting confused. See, I did Einstein just prior to this. Now it's Laplace and Lavoisier. This was in 1905. I could confirm from the book. I urge you to confirm as well. Don't take me as an authority when I quote this. Now, they proved this with an ice calorimeter. The ice calorimeter actually has a outer jacket where there's a mouse, inner jacket, and the outer portion, inner jacket has ice. And the whole experiment comprised of the mouse breathing and ice melting. And of course, we all know this. When we go out in winter, hot air comes out and we get the fumes of combustion, fumes of respiration, which is probably combustion, but then our carbon dioxide is coming out. We're taking in oxygen. So the metabolic fuel, that could be it. But I found the fact that Wikipedia on ice calorimeters had an interesting equation, which was del Q, change in heat capacity, is equal to CT, latent heat of ice, multiplied by the change in volume plus specific heat capacity into change in temperature. I didn't check on the units, and I made this and I did this experiment. I took a beaker, filled it with the ice, measured the mass of the beaker, measured the mass of the ice, measured the mass of the ice. You have to zero it. All right. If you're doing this experiment, put the beaker zero the balance, and then add ice. Only then are you going to measure the ice. Otherwise, you're going to get the beaker and the ice, mass of the beaker and the ice. Your experiment is going to be incorrect. So I measured the mass of ice and then put the ice in 500 ml of water. Put a thermometer in the water, and increase the temperature of the stove to 100 degrees centigrade, and turned on the stove and left it at 100 degrees centigrade. The temperature didn't go beyond 61 degrees centigrade. The ice melted, and I had gotten the density of ice from the web from a reliable source. It didn't kind of add up. I saw some steam come out. So either the density of ice is also 1 gram per mil, it cannot be. Ice floats on water. So it's 0.931 gram per mil, as my source of reference said, and the discrepancy, 14.6 mil, I think. Let me look. And the discrepancy I had was 14.8 mil. 14.8 mil, because mass by density is volume, right? So I measured the volume of water in the ice. And unless, see, conical flasks and beakers are not accurate. I used my cooking measure, 250 ml measuring cup, and unless that is not accurate. But you usually take 1 cup, 2 cups, so that's okay. That should be okay, I think. 250 ml is all right. So 14.8 ml. So the 14.8 ml of water turned into steam, which means that it is reacting with the oxygen in the air, and that the melting ice is reacting with the oxygen in the air and turning to water vapor. That might be it. But this equation for the ice calorimeter, which is on Wikipedia, is wrong because the units don't match up. There's a mil which comes out, which you cannot explain. So I think you have to double. So, but you could, the heat capacity is equal to MCP, mass of the calorimeter water, which is 500 ml by density, which are taken into specific heat capacity into delta T, plus mass of the ice into latent heat of fusion of ice. This I know from my undergraduate degree, because I had done material and energy balances and design as well, design of reactor, design of distillation column. Now if you need to double check if Q is right, then you could consider Fourier's law of conduction. But Fourier brought in the distance either as well. So I would have to assume that the heat was being conducted through the calorimeter water, which is outside the beaker of ice. And I have to assume 10 centimeter or something. It was this much, 500 ml. How much could it be? The vessel was this big, this high, and this big. So diameter of about 8 centimeter, I think, with height of 10 centimeter would be too much. Height was itself. You can do this. You can do this and figure it out. I would have to assume the length. Now, I'm going to measure the vessel and then see. And approximate it. But thermal conductivity needed time. I'm going to assume again it didn't take longer than 10 minutes for the ice to melt. It's going to take 10 minutes. Thermal conductivity is going to cut the length, the centimeter you get from, or is it going to become area? Why don't you try this? I recommend you look at Bird, Stewart, and Lightfoot transport phenomena, their transport phenomena for Fourier's law of conduction, and see if your cues match. It's a fun experiment. You get beakers and conical flasks and graduated cylinder. If you don't trust the kitchen measuring cup, you have to, the weighing scale was kitchen and was my kitchen scale. I urge you to go to Michael's Canada and buy a graduated cylinder as well. Now it's a fun exercise. I'm going to break my head over this and see where the additional seconds and the time and length, time and height units will be cancelled out. But flow is Fourier's law of conduction. This would be mCp delta T plus m lambda would be mass into kilojoules per, let me see if Cp delta T mass into kilojoules per gram. You get kilojoules. Believe it or not, you get kilojoules. Oh, so you actually get Q, heat, change in heat in kilojoules. Or you can convert, it's not a big deal. You can convert it to calories. Fourier's law of heat conduction is equal to Q is equal to minus K dt by dy Q is equal to where K. This is all found out data. It's all in Bird, Stewart, and Lightfoot. K. So you would have to, room temperature. You'd have to consider room temperature, right? It's at 25 degrees centigrade, and the thermometer went up to 61 degrees centigrade. So the delta T is 61 degrees centigrade. But so you would have to take thermal conductivity, both the data at 20 degrees, approximated to 20 degrees centigrade, thermal conductivity at 60 degrees centigrade minus thermal conductivity at 20 degrees centigrade. That would be K. K is easy, but it's a very low value. So I'm getting kilo in Q into 10 minutes. So this heat flow in kilojoules that I calculate kilojoules. You'll get kilojoules would be Cp specific heat capacity, lambda is latent heat of fusion of ice. So this is the calorific water, calorimetric water, And this is ice, which is the so I would get this, but this I should have taken time. I should have taken time. I might repeat the experiment and take time. It's going to be a small value, would be per 10 minutes, per 10 minutes. So there, I would be getting Fourier's law of conduction back. That's all I have to say. Why don't you try it out or talk to your professors about it? All those keeners out there. We had this keener, all right? I used to work on this hyper performance liquid chromatography analytical equipment. And thank you, Professor Chang, for allowing me to use the equipment back during my MASc research days. Um, Another MASc student, but she was from pharmacy. She also used to use it. She was being co-supervised by Professor Chang, and who's a lady, and she had taught me, showed me the ropes around. So we could not get a free time on the HPLC because there was this keener of a fourth year student. Fourth year students should not be keeners, all right? They should let graduate students use all the lab equipment in peace. He would sign up practically every day. And Warren Ferguson. So, anyways, and the last I remember of Warren Ferguson was bumping into him during my work days in the Department of Chemical Engineering in Applied Chemistry, University of Toronto. But briefly, he was working for Professor Cluett then. But during my pregnancy days, I was going to the library, and he said, "One last visit to the library, Gayatri. That is enough. That is done. Enough. How many times do you have to go to the library?" Pleasant memories. I say he shouldn't use the HPLC anymore in his life, but then he switched to process control. So that's okay. And I should go to libraries less. But once I must go, just to prove that the internet is as effective, as wonderful, as special, and as beautiful in scent as the odor of moldy books in libraries and journals. All right? Signing off, Gayatri B. Sitaram coming to you on YouTube. Thank you.